Mike, and this is the Air Leak Wireless Air Detection Group.
I'm Grace.
I'm Luca.
Hello, I'm Yus.
And I'm Brian.
I'm Matthew.
Together.
And we're Air Leak.
Yeah, good job.
Did you know that air leaks can waste between 25 to 40% of the total energy in industrial buildings? This represents a significant loss in both energy efficiency and cost. Current methods for detecting these leaks, such as using sound or cameras, are often inefficient and ineffective. To address this issue, we established specific requirements and objectives for our project to create a system that passively detects where leaks are without any intrusive methods. Some of these requirements include designing a demo that effectively showcases our air leakage detected system, including functionalities for leak detection, leak location, and wireless communication, ensuring deviations from the linear response are no more than 0.5% across the entire measurement range, maintain a noise level less than 20 micrograms per hertz squared, keep cross-axis sensitivity below 2% under various operational conditions, and achieve 95% accuracy in both leak detection and leak location. Overall, our objective is to develop a practical system that records vibrations in a pipe with an accelerometer and wirelessly transmits the data to a centralized system. This system will then combine data from multiple sensors using frequency and time-based analysis methods to accurately detect the location and presence of air leaks along the connected pipe. To tackle this problem of air leaks, we designed a demo that showcases our innovative approach. Our system utilizes accelerometers to detect air leaks in pipes, and after testing multiple accelerometers, including an MMA 8451 and MPU 6050, we selected the LIS3DHH for its low noise, high accuracy, and 3-axis measurement capabilities. The LIS3DHH accelerometer gathers raw X, Y, and Z accelerometer values, meaning when it moves, the accelerometer can pick up on what the acceleration on each axis is. When a leak is present, there's a vibration along the pipe that causes these acceleration values to change, allowing us to detect both the presence and the location of the leak. Later in this video, we'll explain how we use this data for precise leak detection.
So this is our final pipe demo, and this is I'm going to set it up and explain it to you how to do it. So first of all, we're gonna set it to 110 psi, and then plug the quick hose fitting to the pipe. Make sure it's tight and there's no air leak. And then we gotta turn on the air compressor. And then over here there's a air ball valve to control the air going through all the pipe to the end. And over here there's the needle valve. We choose the needle valve as the leak because it is easy to apply and use, and it could create an adjustable and constant leak. And at the end there's an air muffler. It's used to noise reduction and stabilize pressure levels for the air compressor, and also affect the efficiency and longevity of the pipe system design. And as you can see, we all use brass connectors and brass air ball valve because it helps reduce noise frequency for the accelerometer, and it helps gathering the data very well, and it provides tighter seal than stainless steel.
Overall, the software received an wireless data transmitted over Wi-Fi from multiple sensor, and then the computer processed the received data. The accelerometer communicates with ESP32 using the SPI protocol that allows ESP32 to transmit pre-processed data to the server over TCP to Wi-Fi access point, although the server is not directly involved in this process. The server code is written in Python and contains the following steps. Set the network configuration and start with turning on the server, opening the socket on the specific IP and the port, then waiting for multiple client sensor connections.
After starting the server, we reset the ESP controllers to make sure they start up in the power up state. This makes sure that nothing else is set and that the ESPs are clean and ready to go. The ESPs then connect to the Wi-Fi, and this allows them to communicate wirelessly to the server running on a computer. Once it's connected to the Wi-Fi network, it then initializes a TCP connection and is then initialized. After initializing the sensor, or after initializing the TCP connection, it then sends the ID of the ESP. These ESPs have internal flash memory that saves values between multiple restarts and power cycles, allowing us to store data such as an identification number for each sensor, allowing each sensor to be unique and different. Once this value is read, we send it to the server so that the server knows what ID the sensor is. Once this is done, it then creates a specific thread for that sensor.
After watching for an ID to be sent from the ESP32, the server then starts up the thread to handle communication with the sensor. This can allow the sensor to manage communication and data synchronization between sensors. And then after connecting the thread, wait for the other sensor in the pair to connect, after which is sent to the pair information such as IP and ID. And each sensor to have a specific pair, as knowing the distance between the two sensors is very important for localization.
Once the ESP receives the information about its sensors pair, a lot of stuff happens in quick succession. First, the sensors are initialized for each ESP. Using SPI, we check if the correct sensor is connected, as we don't want to read incorrect information and send that to the server. Then we reset its sensor, and once the sensor has initialized itself, we enable it and then set some other values, such as incrementing each SPI address. Once that is done, we have now entered a critical time section of the code. Stuff here is very important, as we're trying to synchronize the two ESPs to make sure that they begin collecting the data at the same time. The way we do this is we send a ping pong between the two ESPs using UDP. The sensor with the smaller ID sends the empty ping packet to the other sensor. That first sensor will be keeping track of the time of flight for the total ping pong. When the second sensor receives the empty ping packet, it then immediately responds with an empty pong packet and then waits for 1 second. When the first sensor then receives the pong packet, it calculates the total time for the ping pong, then subtracts half of this delta time so that the two sensors are as closely synchronized as possible. Now that the two sensors are synchronized, we then collect data from the sensors for a total of 1 second. While each LIS3DH8 sensor only has a reported sample rate of 1.1 kilohertz, we figured out a way to technically record samples at 9 kilohertz. Then, once all of this data has been written to a buffer, we then send a packet to the server containing the length and number of axes that the data contains, and then once that has finally been sent, we break the data up into packets with a max length of 2,000 bytes due to limitations of the ESP and send it to the server.
Receiving data and saved to file, as the sensors stream the data to the server, the data is aggregation into one large buffer and then saved to timestamp file specific to each sensor. Using a lock, only one sensor thread can save at a time. The first thread to save also as the file path to a thread segment. The second thread to save takes this information and use it to update the list of saved samples, which allow us to look back at the data. And once the file have been saved, the file paths and some additional information are sent to the rendering and computing thread to process and visualize the data for analysis of the result in real time. The render threads show one Fourier transform and one raw data, and then the server can help to detect error leaks, so we can provide the system with high reliability and accuracy.
Our machine learning model is a convolutional neural network designed to classify accelerometer data to detect presence of leaks. The process involves multiple steps, from data preparation to model training to evaluation. So first, we collect data from different days, and we process them and we load them. Then the data is plotted to ensure uniform math, and each data sample is centered by subtracting the mean to normalize the input. Then we use Fourier transform to convert time domain to frequency domain to ensure to highlight periodic patterns. Then this process data is combined into a consistent format that is suitable for the model. So to address the issue of class imbalance, we use the oversampling technique to ensure the minority class is sufficiently represented during the training, preventing the model from being biased toward the majority of class. For the model architecture, there is 4 layers. The model starts with a convolutional layer that applies filter to the input data. These filters help in automatically learn the spatial hierarchies in the data, such as detecting edges, textures, and more complex patterns. Then a pooling layer follows the convolutional layers to reduce the dimensionality of the feature maps, making the computation more efficient and reduce the risk of overfitting. Then we have the dense layer that are used to interpret the high-level features and make the final classification. And then to finish, for the 4th layer, the output layer, which uses a signal activation function to produce a probability score for the binary classification task for leak or no leak.
In addition to leak detection, our project also incorporates leak location detection, which works like this. We can measure the delay between the 2 packets we get from each of the sensors using correlation. With that delay, we can multiply by the speed of sound in the pipe to get the difference in distance between the first sensor and the leak and the second sensor in the leak. Knowing that, with a little bit of algebra, we can find the distance from the first sensor and the leak. This method works in theory, but in practice, the sensors we have don't sample fast enough. So an off by 1 error for correlation detection can lead to a large error in localization. Instead, we went with the machine learning approach, which is able to learn the profile of our setup and estimate the leak that way.
The leak is currently closed.